Now to talk a little bit about carbon. We have both a long-term and a short-term carbon cycle. In the long-term carbon cycle, carbon is removed from the atmosphere, from the oceans, and from the biosphere, and stored for millions of years in the lithosphere. It leaves through the lithosphere through volcanic eruptions, which is a naturally occurring thing, and through the burning of fossil fuels, which is something that humans do. It is moved through weathering and erosion, and through the burial and preservation of organic materials. In the short-term carbon cycle, the carbon moves pretty quickly among the major spheres of our planet. Most of the carbon in the short-term cycle resides in the ocean. This figure from your textbook depicts the natural transfer of carbon dioxide between the lithosphere and the atmosphere. Natural atmospheric carbon dioxide concentrations have changed very, very little in the last 800,000 years, because the same amount of carbon that enters the atmosphere through volcanic activity is removed from the atmosphere during the weathering of rock. Weathering of rocks removes carbon from the atmosphere when carbon dioxide in the atmosphere dissolves in rainwater. It forms carbonic acid. This reacts with minerals in the rocks, particularly silicate minerals, and converts them into bicarbonate CO2, which is a stable form of carbon that is then transported to the ocean via rivers and runoff, where it can be stored for really long periods. This image is just showing you the same thing in a little more detail. So that was natural long-term transfer. And then we throw people into the mix. Human activity has greatly accelerated how we transfer that carbon from the lithosphere to the biosphere to the atmosphere, specifically by burning so many fossil fuels and by stripping forests. We have essentially added one additional thing, a really large thing, that moves carbon from the lithosphere to the atmosphere far more rapidly than would occur naturally. Human activity adds about 35 billion metric tons of carbon dioxide to the atmosphere each year. If we take all of the human activity, we emit an average year's worth of volcanic carbon dioxide emissions in just 4 days. We burn a lot of stuff. And when we cut down forests, the carbon stored within those trees enters the atmosphere. So we are adding multiple different layers of greenhouse gases to the air. This is why human activity is blamed when it comes to climate change. It's not that human activity is inherently bad, but there is a definite recognition of our overall impact on the climate system. Now, armed with that background information, we are going to talk a bit about our current climate and consider the crossroads that we find ourselves at. Because human activities have caused our carbon dioxide concentrations to rise in the atmosphere to over 400 parts per million, and our current rate of increase is roughly 2.5 parts per million per year, this has been dubbed the anthropogenic greenhouse effect. Human activities have added enough greenhouse gases to the atmosphere at a fast enough rate that it is actually impacting the planet's overall greenhouse effect, and it's causing our overall global temperatures to warm up. The Keeling curve, which you saw earlier this semester, is a graph that shows the steady rise of atmospheric CO2 levels since 1958. Based on measurements taken at Hawaii's Mauna Loa Observatory by scientist Charles David Keeling. The curve highlights seasonal fluctuations and a long-term upward trend. It has become a key indicator of global climate change and a foundational data set for climate science. We know that before 1800, our carbon dioxide concentrations were much lower than they are today. We also know that temperature and carbon dioxide concentration have risen and fallen together over the last 800,000 years or so. This is a picture of the Keeling curve. If you look on the left here, you can see how the little green line decreases and increases every year. This is associated with the growth and decay of organic material. When plants grow in the summer, they absorb CO2 from the atmosphere. leading to a slight decrease in atmospheric carbon concentrations. But in winter, as the plants stop growing and some decay, they release carbon dioxide, which causes atmospheric carbon dioxide levels to rise again. Thus, these seasonal fluctuations, the rise and fall, are just a typical reaction to our normal seasonal changes. We do see, in looking at this Keeling curve, that it shows an overall increase from the late 1950s. Mind you that this is just a tiny little snapshot of time overall. If we looked at CO concentrations over a really long time period before this graphic, you would see that we still see the same similar decreases and increases. What's noteworthy about this is the upward trend we're seeing, how quickly it's come on, and the reason we think is behind it. Here you can see a picture of one of those ice cores that we might use to reconstruct temperature from. From these tiny little ancient air bubbles that are trapped in the ice, we can get ice cores from places like Greenland and Antarctica, basically any place we have large areas of ice sheets, to look at past atmospheric CO2 concentrations. The graph at the bottom here is showing you that overall change in the most recent time period, and then around 1860. Not long after the Industrial Revolution and we began burning fossil fuels, our carbon dioxide concentrations began rising, and very quickly. Here what we're doing is we are comparing temperature and carbon dioxide concentrations over the last 800,000 years. And you can see how they typically rise and fall together. This is why we are concerned about the current anthropogenically caused climate change. Our CO2 concentration is increasing so much that it's causing temperatures to rise to a level we are not accustomed to dealing with or are prepared to deal with. If it continues to rise, some serious questions are what will be the actual environmental effects that will ensue, and what do we do after that? So let's talk about the anthropogenic greenhouse effect. The anthropogenic greenhouse effect is the idea that human emissions of carbon dioxide and other greenhouse gases like methane are creating an additional enhancement of the natural greenhouse effect and ultimately changing our atmosphere. We looked last lecture, I believe, yes, at the Arctic and the ice albedo positive feedback. We're going to talk about that a little more because it is very, very important. Research indicates that the Arctic is warming at twice the rate of the rest of the world. You might be wondering why. The tropics cannot get any hotter due to how the Earth system functions. So all that additional heat that's being added to the system has to be redirected poleward in an attempt to balance the latitudinal surface heating differential. Remember, all the Earth's surfaces want to maintain equilibrium, and they are constantly adjusting to try to get that nice balance. So as that heat is redirected poleward, with more energy at the poles, these locations are warming. And by melting ice, we dramatically change the albedo and the reflectivity at the poles. What we now have is a system that is warming faster and faster, melting more and more ice, and further enhancing the melting process. Remember that ice albedo feedback. Here we've got a graph of temperature anomalies since 1880. Remember, a temperature anomaly is one that varies from the normal, the average temperature. We were a little cooler back at 1880, and then we began to warm up. But we really began to warm up when we started to develop different areas around the world that had not been developed industrial type countries before. They were primarily agricultural, like say China and India. once those areas started developing right around the 1940s, we start to see this real bump in warming. In the most recent decades, you can see that our temperatures have been increasing very quickly. This is a map of those temperature anomalies. You can see very clearly the dramatic increase in temperature experienced in the Arctic as compared to pretty much everywhere else on the planet. Now, a 4-degree temperature anomaly means that these locations are 4 degrees warmer than their global average. The global average is taken for this map was taken for 1951 to 1980. So anything that is above or below that average number for that location would be considered an anomaly. If the anomaly is lower, which you don't see a whole bunch, but we do have some of that, there's a slight cooling trend indicating that it's actually getting a little bit cooler in those locations. In the areas with the brightest colors, like the oranges and the reds, the temperature is 2 to 4 degrees above its normal average temperature range. This means that according to this particular map, which represents averages from December 2003 to December 2013, the Arctic is 4 degrees warmer than it was during the previous 3 decades. Our current temperature is higher than it has been at any time in the last 1,500 years. Now, a major point of debate among climate change skeptics is that we have no other explanation for the cause of climate change other than us. We know why, or at least we're fairly confident that we understand why, the climate has changed in the past. When factors like a massive ocean circulation are disrupted, or the sun alters the amount of energy it emits, or our orbital relationship with the sun changes, or a significant volcanic eruption occurs, all of these things can lead to changes in the climate. But right now, none of those things are happening to any degree different from they normally do. And I will show you an example shortly where we see how none of these things actually point to this. So the question then becomes, who or what is the cause? Could it be us? Yep, could be. Here are some more temperature graphics highlighting the uniqueness of our current increase. Figure B, which you've seen previously, shows the past 800,000 years. Figure A takes the last 15,000 years and zooms in, illustrating how that small section appears when it's smoothed out, that small section of time. You still see fluctuations throughout each year, but then suddenly, right around 1880, when we began recording temperatures, there is a dramatic increase. Now, someone might question why we feel confident in these temperatures. That's a valid question. We are only reconstructing them based on the gases present in various ice cores and other proxy methods. Fair enough. But we always consider error and uncertainty when estimating these types of things. Even so, that blue reconstructed temperature line is higher than it has been for at least the last 250 years. So whatever the reason, we are getting warmer. These graphics are showcasing different mechanisms that have been proposed for perhaps contributing to or causing the current warming trend. First, before we go through these, let me draw your attention down to the graph on the bottom. This is our temperature trend. So we want to compare all of the mechanisms that we show here to that to see what's going on. Things like El Nino, which was described in chapters 5 and 6 of your textbook, which you hopefully read, or some of the other factors that have been discussed earlier, don't appear likely to have produced the warming trend we are currently experiencing. We don't see many massive volcanic eruptions lately, and even those that do occur typically lead to a cooling period. However, those volcanoes are not cooling us off. As for sunspots, We are actually in a weak period of sunspot activity right now. That being the case, we shouldn't be getting warmer. We should be getting cooler, but we're not. And El Nino has really not ever produced a lasting temperature trend, so there's really nothing for us to point the finger at there. This is why scientists have fairly high confidence that the warming trend is linked to human activity. Climate change is often portrayed as entirely negative, but that may not be entirely accurate. Like most issues in life, there can be both positives and negatives involved. Some aspects of climate change might be beneficial while others might be detrimental. The difficulty is that as scientists, we are not exactly sure to what degree all these changes will occur. So we're going to look at a few of those positives and negatives and the things that we believe are going to be impacted by climate change. We're going to spend a bit of time on these slides because there's a lot to go through. So, because we are not sure of exactly what to expect, that is why the Intergovernmental Panel on Climate Change, or the IPCC, was created to bring scientists together to address those questions. In general, we believe some areas will experience increased agricultural output while others will see decreases. This is our first impact we're looking at. You might imagine that if the climate shifts towards being a little bit warmer with a little more moisture, that in areas that currently lack sufficient levels of those things to grow crops effectively, it would enable them to grow more crops. You might also envision the potential for some negative changes, but it seems globally, in general, this would be a positive thing. We could also consider the changes to the Arctic. Well, thanks to the melting, a completely new Arctic has emerged, for better or for worse, leading to a new Arctic economy centered on shipping, fishing, tourism, petroleum, and natural gas exploration. In fact, nations are placing flags on the Arctic Ocean's seabed in attempts to lay claim to it. That's not really how that works, but people are certainly trying, because we are just greedy little buggers like that. If you take a look online, you can find some interesting information about our new Arctic. Sea level rise is a significant concern for Louisiana and most southern coastal regions. Sea level rise results from two different factors. First, the fact that warmer water expands just like air, causing it to occupy a slightly larger volume. So we've got that going on. Secondly, we are melting a significant amount of ice. It's not that the ice that's already in the water that matters. Consider your glass of water with ice cubes. When that ice melts, it doesn't overflow, right? Well, it's not the ice on the water that's causing the issue. It's the ice that's on land, like in Greenland and Antarctica, that is actually melting, flowing into the oceans and contributing to rising sea levels. Here in Louisiana, we have a particularly bad problem because we are sinking. There's a big long explanation for why that is, and if you're interested in it, I highly suggest that you take Geog 2051 because they will teach you all about that. So while there is this big long explanation for why this is occurring, the simplest one is that we have messed with the Mississippi River too much. We redirect it, we levee it, and we try to make it stay in one spot. But a river system naturally migrates in one direction and then another direction over thousands of years, and we have locked it in place. This has disrupted the normal sediment deposit patterns, those that built the Mississippi River Delta, and they are not functioning as they used to. And so, we are sinking. Sea level rise is also a threat to other nations, particularly like island nations, and then very low-lying areas like Bangladesh and the Indian Ocean. Remember, we talked about these people experiencing like extra levels of hurricane hazards just because of their very low-lying position. These low-lying areas will flood more frequently and more frequently experience bad weather under climate change. So on that note, let's consider how hurricanes might change in a changing climate. If more heat is added to the system, well, then we can evaporate more water. And as we learned in the lecture on hurricanes, heat and water are fuel for hurricanes. All else being equal, this should logically make things worse, and that's actually what we are seeing. Events like Hurricanes Florence and Harvey, Maria, and Laura, those really big impact events, these are all events that individually maybe cannot point a finger at climate change. But if every single event that occurs, like those really bad events, is starting to get a little bit worse and worse and worse every time, and there are more frequently those very bad events, you might say that the hurricane climate itself is changing. Extinctions are something to be considered as well. Without ice on our planet, we don't have polar bears, and our ice is melting. Polar bears are just one of any given number of poster children for climate change extinction that we can come up with. How about bees? We are seeing huge die-offs in bees. And if you really think about it, bees pollinate and are necessary for food production. Not everything needs a bee to pollinate, but they sure as heck help. So, if we lose polar bears, as dark and dismal a place as the world would be without those little cute, cuddly, fishy-scented murder machines that are polar bears, life would still go on. If the bees go down, we're hosed. And what about plants? Think about all the plants that can't get up and move around. They can't pick up their little feet and run when climate change is coming their way. They may not be able to shift their locations fast enough through seeding and reseeding to deal with what's coming their way. And if these climate shifts come that they cannot adjust to, they will die. There's all sorts of amphibians, coral reefs, insects, you name it. We have a very diverse and kind of frighteningly diverse range of potential extinctions looming. And then finally, we anticipate potential shifts in wind and precipitation patterns. We are unsure how that will affect things. So that is also something to be considered. Here's that graphic showing you the new navigable Arctic. The Northwest Passage and the Northern Sea Route offer considerably shorter, faster, and less expensive routes for shipping and traffic between the Atlantic and the Pacific Oceans. Before 2010, those routes were mostly covered with sea ice, even in the summertime. Now that it's melting, the shipping routes are open for traffic, and this is really a big deal to be able to go all the way over, and you end up making it through much cheaper and much faster than you used to be able to do. From an economic standpoint, at least, this is great. However, you can already see the potential for overuse and exploitation, as we tend to do, even though we know better. This particular image, this book was published, I don't know, a few years back, so this is kind of a dated image, but if you look at the numbers, you get an idea of why I'm saying we have a potential for misuse. In 2010, only 4 ships could make it through the passage due to the sea ice. In 2011, 34 made it through. In 2012, 46 made it through. But then, because of the melting, in 2013, 400 ships made it through. And then 10 years later, that number is closer to 700 ships. That's a huge difference. And you can be sure that it did, has, and will continue to have a huge environmental impact. And what about glaciers? If you're going to go see a glacier, you better go now, because they are melting rapidly. The top graphic on this slide shows the overall change in the length of glaciers all over the world, wherever those might happen to be. They are all melting, and not just melting, they are receding. If we look at these 2 photographs at the bottom of the slide, these are comparing the same glacier over a period of time. That black and white photo on your left was taken in 1941. We got a nice healthy glacier going there. But only a few short decades later, that ice has melted, it has formed this massive lake, and it has receded up into the mountain pass. Obviously, warming temperatures are going to have a major impact in this type of environment. So at this point, the billion-dollar question is there a way for humans to actually stabilize the climate? What does that even mean? Well, the climate scientists working on this question propose that if we can limit our carbon dioxide concentrations to less than 500 ppm, parts per million, it could help avoid quote unquote significant climate change. To achieve this goal, we would need to cut our emissions by 80% within the next couple of decades. And that's just not going to happen. That goal is too ambitious, it's too rapid, and the moral of the story is that we can't stop it. But we can do something to slow it down or adapt to it. Can we do this? Absolutely. So here's a table that provides some examples of how we might limit carbon dioxide concentrations on a really large scale. This includes things like improving the efficiency of cars and advancing technologies for burning coal to reduce atmospheric pollution, increasing solar and wind energy production, and ceasing deforestation in tropical rainforests. This part is vital as it severely hampers our ability to regulate the atmosphere for our benefit, for every living critter's benefit. So these are some of the ways that international, national, and local changes can be made. Things like increasing the efficiency of cars and taxing or fining people who overuse carbon, burn it to excess, increasing the use of carbon-free energy, and making personal choices. There are a lot of people on this planet, and if we each individually act towards understanding what needs to be done and trying to be a little bit better at doing that to help rein climate change in, it will make a difference. Will it make a massive difference? Well, it's not going to stop it, but it will slow it down and give us more time to adapt to this new atmospheric environment we have created for ourselves. So what you're looking at here is an example of where people are actually using something known as urban agriculture to try to reduce their greenhouse gas emissions. A lot of times you'll hear this referred to as green space in metropolitan areas and cities. This is something I'm super interested in. And one place that's doing this like to the max is Toronto, Canada. Toronto, for example, has the goal of reducing its carbon emissions by 80% by the year 2050, and they're actually getting pretty darn close to that, just the city itself. Of all places, Chicago is a leader among American cities in reducing carbon emissions. For example, they have planted rooftops like the one you are seeing here that decrease carbon emissions by lowering electricity use in the summer and helping to retain warmth inside that building in the winter. What we're seeing here is shown on top of Chicago's City Hall, which was the first rooftop garden like this on any municipal building in the US. Rooftops like these not only improve energy efficiency, but they also provide a place for people to go and walk and let off some steam, bring in some fresh air, and enjoy a little green space during a busy workday. Now, that might not seem like that big of a deal, but it makes a huge difference to the wellness and well-being of your workforce. If your workers are happier and a little more emotionally and psychologically well-adjusted, well, then they'll be happier and be more productive. So if you don't care about the moral reasons for working towards stopping climate change, or curbing climate change, consider the economic benefits instead. And for those of you who do care about the moral implications, well, this is a win-win compromise where we can genuinely work towards, in the future, where both the environment and the economy benefit. Each of us has something called a carbon footprint that collectively represents the total amount of greenhouse gases generated through all of our different daily activities. There are a couple of really good websites online that you can go and visit to calculate your carbon footprint, and it's going to take everything you do into account. So things from how much water you use when you brush your teeth to how you transport yourself from location to location, what kind of food you eat, what do you do with your waste, do you recycle? All of these things add up to how much energy you actually use as a human being every day, day after day, year after year. That's your carbon footprint. These are some really interesting sites, and I will try and find a few of them and post those links up on Moodle if you would like to try this out and see what your own carbon footprint amounts to. It can be pretty shocking. But you have to use energy, right? You need it. However, there are ways that you can reduce how much you use if you stop to think about it. The catch is that many of us just take energy for granted. We're raised in a world where energy is thought of as a constant source on demand. You need to use some kind of electrical appliance, you flip a switch. Your car starts to run out of gas, you go fill up your car. It's just we totally take it for granted. But that's not something that is sustainable. It is not something that we can continue to do. We are now getting into a world where it really matters that you pay attention, because we're going to run out of all those energy sources. And that's going to be a big problem. So how do you reduce your energy use and your unsustainable practices so that we can help make it a more equitable, sustainable environment for everybody? Well, it's those good old 3 R's: reduce, reuse, and recycle. That's it. It's just about the idea of we're generating too much waste, so don't use so much stuff if you don't need it. Don't go do silly things that are just a waste and using energy for no good reason. Carpool. Take the bus, which a lot of us here do, or we bike, or we walk into school. I myself walk into school. I cannot do that at home because I am 60 miles from the nearest school. So use a lot more energy when I'm at home than I do here. If you entered in your home energy into those carbon footprint sites, you would be perhaps absolutely shocked at how much energy you actually use. So there are a lot of things that you can do to help reduce that. There are ways to reduce your water use. There's so many different ways. You could catch water outside. Don't leave your sink running when you're brushing your teeth or washing your hands. If you are strictly using electricity and you are a homeowner, or you have any say in your parents or your landlords, how they are setting things up, you can use solar energy or wind energy. You're seeing a lot more solar panels on people's houses so that they're not having to pull as much off the coal and hydroelectro power generated grids. Energy-wise, that's a much wiser choice. There are so many different ways if you stop and think about it. And the biggest thing that I can end this lecture with is to tell you to just think about what you do. Where are the resources that you are using coming from? What is it costing you environmentally, economy-wise, to use those things? Is there a way, a better way, than you can go about using them? So if you just stop to think about things and really give it some thought as to what you can do to help, then you are being active. And that is a win-win for everyone. And that's the end of this chapter.